Hello and welcome to today's webcast with Freemelt, where CEO Daniel Gidlund, CFO Martin Granlund, and CI lead Per Voxenius will present the report for the third quarter of 2024. After the presentation, there will be a Q&A, so if you have any questions, you can submit them into the form to the right. And with that said, I hand over the word to you guys.
Thank you. So, hi and welcome to our Q3 webcast. In today's webcast, we will start by giving a bit of a short recap on who Freemelt are and also the strategic plan that we are executing on. As if you've been here before, you also know that we deep dive in some strategic topic during this webcast as well. And this time we will focus on various development projects that we are working on and what they mean for Freemelt and also our growth journey ahead. So on this call, we have, except for myself, our CFO Martin Granlund and also our CI lead Per Voxenius, who is in charge of our continuous improvements program and especially the industrialization of Freemelt. So with that said, I kick off. So Freemelt was founded in 2017 by 7 engineers with extensive experience from both additive manufacturing but also electron beam powder bed fusion technology, mainly them from the company Arcam, which was another successful Swedish 3D printing company that the GE acquired in 2016. So what we do is to develop advanced 3D printers for metal components, aiming to be the leading supplier in additive manufacturing by leveraging on our EPBF technology. Our focus is in areas where 3D printing offers significant opportunities and value, particularly in the industries such as defense, energy, and medtech. And these are also industries where complex and high performance components are in demand. If you look into our technology, it is independent on materials, but our primary materials are tungsten with a melting point of 3,400 degrees. So that makes it ideal for advanced defense applications and also fusion reactors in the energy sector. The other material is titanium, which is perfect for implants, and then we have copper, which is highly suitable for applications in need of high connectivity. These materials and applications is where our modular printers using EPBF technology offering significantly higher efficiency compared to other machines on the market. And I think this has also been valued by our customers so far and has resulted in 28 machines that we have sold since the start. From a go-to-market perspective, we have a two-way go-to-market. So one is that we go through the academia to really enable the industrial adoption by both developing then the material processes and also the application for the industry. And then we go also direct towards the industrial customers as well. If you look into our 2030 strategy, I mean, our goal is to achieve 1 billion revenue by 2030 at 25% recurring revenue from the aftermarket business. But long term, we aim to have more than 40% coming from the aftermarket. Now we are pursuing several strategic initiatives to reach this target. And I think here, where our R&D efforts are closely aligned with our research institutes and also the universities that we work with, which will enable us to drive efficient adoption of additive manufacturing within the industries we target. As I said before, I mean, in parallel, we focus on direct enterprise sales, and we are also establishing a local presence in strategic markets like Europe and also North America. And to put some further context on this, let me explain and maybe zoom in on an industrial customer that is having serial production operation. And let's also assume that this customer is using traditional manufacturing technology at this moment when they're manufacturing parts. Then it requires two development steps prior to entering into the industrialization phase. And when they start to ramp up into serial production, through additive manufacturing. For Freemelt, the large volume sales of machine will come when the customer is ramping up his serial production. But the good thing for Freemelt is that we have a business opportunity in each of those steps that you see here on the screen prior to entering to serial production. And it can either be related to that we sell a project like a feasibility study or a proof of concept where the industrial customer order this project from Freemelt, or it can actually also be through our partners like universities or research institute. If the feasibility study for the industrial customer is successful, then it moves into a proof of concept. And there the industrial customer itself either purchase an eMELT machine or can rent the eMELT to really run the proof of concept and to achieve those expected KPIs as well that they have. So I think here by supporting the entire customer development journey, then we also position ourselves like a long-term partner, and I think we also ensure a much more smoother transition and also a faster product time to market for the customer as well. So hopefully this explanation gives you a bit more flavor as well on those different kind of steps and projects that we have announced recently as well. And Per will actually come back and give some further explanation later on as well. Okay, so let's then zoom in on the achievements in Q3. We have received feedback to be more transparent regarding the various paid customer projects that we're engaged in as well. Because these are actually really critical indicators for our upcoming business towards industrial serial producing clients. And during Q3, we launched 6 new feasibility studies or projects, and we successfully completed 4 projects. And I think this is demonstrating an increasing pace of our innovation. For example, we finalized the first phase of a study with Saab for defense application. And this is about validating our EPBF technology and the potential for producing high performance and complex components in the defense applications. We have also made significant progress with other feasibility studies that has been ordered during the quarters as well. UKAEA, so this is the United Kingdom Atomic Energy Authorities. Here we are actually at the second phase of feasibility study. And now the focus is really on the tungsten tiles for fusion reactors. And I think it's also important to highlight the progress with Sandvik and Mid Sweden University as well. So this cooperation is really to develop material processes for chemically reduced tungsten powder. And why this is important, because it's really about to become more cost efficient in manufacturing fully dense tungsten components. And I would say that one of the biggest obstacles for the additive manufacturing industry so far has been due to the high powder cost. So this is really why this is so important for us. You know, when we can achieve this process, it also means that we can offer substantially reduced cost per printed part to the customer. And I think it's also worthwhile to mention that thanks to this cooperation as well, then we have secured 100% European supply chain of tungsten powder, which is also critical. And then last but not least, the increased interest and also the demand in US has actually made us force the establishment of a US application center, in this case in cooperation with Hammer Industries. And here the focus is on defense and energy applications. During the quarter, we also achieved a major milestone regarding our industrial offering. When we successfully installed our first eMELT machine at WRM in Italy. So WRM, they are a competence center for implementation of additive technologies to industrial clients. And And actually, after having that installed, we also had our first customer reference visit during September at the site of WRM, which resulted, I would say, in the biggest commercial breakthrough ever for Freemelt after the quarter, when we secured an order from a global orthopedic implant OEM. And what they're going to do a proof of concept on serial production capabilities using eMELT. So this order is a major milestone for Freemelt, and it also strengthened our position in the medical sector and represents which represent actually the sector as well, or the industry that has the highest adoption of additive manufacturing for serial production. If I zoom in on a more general business perspective, we continue to engage with academic customers in both Europe and North America. And I think what we start to see as well, that we can harvest somewhat from the pipeline that we have established over the past year. Why it was rewarding that we finally got 2 of the Freemelt ONE machine orders in the quarter, one in Europe and one in North America. Coming back a bit to the projects that I mentioned before, we currently also running 11 paid customer development projects, and where one has actually transferred from feasibility study into a proof of concept. And I think this is also then reflecting the steady demand for our technology across various industries. So looking ahead, we expect the continued growth in demand for feasibility studies and also, of course, proof of concept projects. And I think this is really telling that more companies are recognizing the value of our technology for industrial applications as well. So this increasing market engagement position us now to transition more of these projects into serial production, where larger scale opportunities and the bigger revenue streams lie as well for Freemelt. If you look into throughout the year, we have so far initiated more than 20 development projects, and we have successfully concluded 10 of them. This ongoing project pipeline, I think, also underscores the growing traction that we are experiencing now in key sectors like defense, energy, and then also medtech. And I think what is evident as well is that our leading position in tungsten, it has generated a lot of interest and also traction. And I think here what you can see as well, that roughly 75% of all the projects that we have been starting during 2024 has been with tungsten, and 60% of all these projects are within defense and energy application, where we also have established a very strong position. So this consistent influx of new projects highlights the expanding interest in our technology and services. So with that said, I will hand over to Per, who is responsible, as I said, for continuous improvements. And Per will share some further details and examples also how the process towards serial production realization works, and how Freemelt cooperate with customers during that entire process. So please, Per.
So again, I will talk about feasibility studies and why it is so important to really adopt AM. When we started developing the eMELT series industrial systems, in parallel, we started to really focus on feasibility studies and really engage with customers. And I will give 2 examples. One is for tungsten, it's plasma-facing components in fusion reactors. And the titanium, I will focus on orthopedic implants. So why do you want tungsten in fusion reactors? It's, I would say, quite simple. It's one thing, it's the high melting point. The other thing is the excellent radiation shielding. So tungsten has the highest melting point of all materials. The good thing is that it really shields very well from heat. The bad thing is that it's almost impossible to manufacture with traditional methods. You're very limited in material properties. You're also very limited with the shape you can do. Since tungsten is the material with the highest melting point, you can't really cast it. I usually say it's like boiling water in a kettle made of ice. The kettle melts before the water boils. So you really can't do it. But we have shown with additive manufacturing that this is a possible way forward. So if you look into the example, fusion reactors, ITER is the world's largest research project. It's a 20 billion euro project. And it has, it's a so-called tokamak, and it has a big volume where you have plasma at 150 million degrees. So it's extremely hot. And you need something that shields from the worst heat, and that is called first wall components or first wall panels. Most people think that this is something that will happen in the future, but actually ITER is being built right now, and they will have 440 panels, each 1.5 square meters big. And already 2 years back, ITER ordered 60 blankets from 2 European suppliers at roughly 100 million euro each. So these are really high value components. The design was ready, they knew how to do it. It was going to be made in beryllium, the first wall of the first part of it. But last year, they decided to switch from beryllium to tungsten. That was a very late decision they made. It was actually thanks to whistleblowers they decided to switch materials. And then we come to the volumes. ITER will need roughly 1.5 million tiles. They are already producing the blankets, they produce the parts. They are putting them in stock, and they are waiting for materials methods to produce them. So again, our focus right now is to learn about materials development. So again, in 2023, ITER decided to shift to tungsten. They decided to use traditional methods, not to use additive manufacturing, because they said it was too late. But at the same time, UKAEA, the United Kingdom Atomic Energy Authority, the UK organization that builds fusion power plants, they wanted to make a first study to understand additive manufacturing, understand if it is a feasible method to produce parts. So we developed, made bulk parts and produced, and this was highly successful. They were very happy with the results. It will be published quite soon, the data, but it is extremely good compared to laser-based method. It's very good compared to traditional methods. And that led to a second study. Quite often a second study is, can you please repeat? But the second study in this case is really about moving the technology forward. They zoomed in on some of the tests we've done. They zoomed in on some of the technologies, specifically spot melting. And that is a study ongoing, but it will be completed in a few weeks' time. That has led to we have sold two systems to university in the UK, both focusing on tungsten, both focusing on this because of the support from UKAEA, and also that they have a very typical customer that can use. It has also led to that we have 2 new feasibility studies at the later stage being done, one for US customer, one for European customer. Those 2 studies have been with quite complicated shapes, quite complicated details. So it's not materials development, it is more application testing we are doing. So what has happened since then? This summer I was at a meeting with something called Fusion for Energy. It's the European part of ITER, the fusion power plant. They told us in June that your technology is interesting. We're interested in it, but it is too late. It will not be included in ITER. But what has happened afterwards, when they have started to see the results from UK, they've seen what we are doing and see our capability, and specifically, they see our productivity. They have decided to see if AM is a way forward for the fusion power plants for this generation and future generations. So they will release in November what is called a TDP, Technology Development Program. They have decided on 2 projects, the 2 most important ones for the ITER power plant. One of them is tungsten for first wall components. So they will investigate if it is possible to use AM in first wall components, because it is a high quality and it is probably at a lower cost compared to traditional methods. And we hope that we have a chance to take part of that. And it would have not taken part if it wasn't for the first study we started last year. And now we are looking into making scalability studies. We are not pushing customers to do this. We have customers coming to us, asking us to do scalability study to see if this is feasible for large power plants and large volumes. We can of course not disclose who it is, but we really have pull that people are coming to us and ask about the possibility to produce tungsten at scale. So again, fusion reactor is actually happening right now. People are really building on it, and of course the knowledge here is directly transferable for the defense sector as well. So it has also led to a number of defense work as well. So that is in short on tungsten and why feasibility studies are so important. Titanium is a different thing. It's a material with much lower melting point. There are different methods to do it. It is a known technology, and all large OEMs use AM. All orthopedic implants OEMs use additive manufacturing. It's already in place. It's already in place in the high value parts of the implant sector. The driver in titanium is porous structures, combining that with solid parts. And you want that because it supports bone ingrowth and you get a longer life of them. So why does OEMs want to make feasibility studies with us? It is a number of reasons, but primarily second source of manufacturing equipment. They want to be able to have more than one supplier. They want to increase productivity and also increase productivity per square meter. They also want the technology more industrialized compared to traditional additive manufacturing. And that's why the ID is so well. And finally, new product development. For example, if you look at the part up to the left here, to the left you have a hip cup, which is a standard part right now in additive. The right is a femur, or it's a hip stem rather, and that is not in additive right now. So that is a possible product moving forward. The same for knees, there are some interesting components there. So what we have been doing in titanium is that, like last year, we developed bulk properties, solid material properties, but also the properties for porous structures. And we have shown that we fulfill the requirements for orthopedic implants, the size of the struts, the size of the holes, so that it is suitable for implants. And that in turn has led to that in this year, what we have really shown that in larger volumes, that we comply to all material standards. And as Daniel said before, we have made a breakthrough with one OEM starting to investigating our technology. Of course, we have worked with them for quite some time, but now they're really investing in our technology, investing in the feasibility study. And that has led to that now with them, we are making a proof of concept study that will be completed next year. So that really, I think both cases, tungsten and titanium, really show the importance of feasibility studies, how it can drive us moving forward and lead to more sales. And again, each new step we see with OEMs right now, they want us to take the next step, not making more test parts. They want us to make really proof of concept. They want us to show that we are productive enough. So we are moving to the right in this scale, into production scalability and into production further on. So I think that completes my presentation on feasibility studies.
Perfect. Thank you very much, Per. Let's move into the financial, Martin.
Thank you, Per. Thank you, Daniel. So I'm going to focus on top line, focus on sales for this presentation, and put a bit more color on what you perhaps have seen in the quarterly report already. On the upper right-hand side, you see a stacked area which represents sales. The dark green part is machine sales that represented 86% of the net sales booked in the quarter. We see a healthy rebound, so it grows both year on year, it grows quarter on quarter. There were 2 machines deliveries in the quarter, which we booked. That's one to University of North Texas and another machine to the University of Birmingham. It's important to note that we in the profit loss, we book sales when the final invoice goes out. How we typically invoice customers is that we ask for a 30% down payment at the purchase order. We invoice 60% at delivery, and we invoice the last 10% after a successful installation. So there is a lag from the PO to booking the sales in the P&L. If we then focus on the aftermarket, these are spare parts and service contracts. It is a small part of sales. It's going to grow over time as the install base increases. It's also going to be a larger part for the industrial machine, which we expect to sell going forward, because it's going to require more of service and more of spare parts and aftermarket, as the utilization rates are much, much higher for those kind of machines. Then we also have the gray part, which is other, and that's where we see the feasibility studies that Daniel and Per have talked about as well. So revenues right now are small, but in the end, we expect some of these feasibility studies to result in machine orders at the later stage in time. So as you see, the sales mix is still very transactional. Every machine sale is a large contributor to sales, and this quarter was two machines being delivered. So turning to the order book. So definition-wise, what we call the order book is where we have received purchase orders from customers, but we haven't yet invoiced those purchase orders. And that can be for different reasons. It can be because it's the invoicing terms that it's up on completion. It's also the invoicing terms I mentioned for the machines, where we only invoice partially in the beginning and over time. And we see the order book at almost 12 million at quarter end. So that's also a growth quarter on quarter and a large growth year on year. Again, the main part of this figure, around 80%, is related to 3D printers, to machines. And a smaller part is related to services and feasibility studies, etc. And what happens is, so we present this order book figure, and after the invoice, then the amount becomes a receivable. After that, it becomes cash flow, and at the very end, it becomes net sales in our profit loss statement. I think I'll stop there and hand it over to you, Daniel.
Perfect. Thank you, Martin. So let me wrap up this Q3 webcast. I think the scalability that we have shown in our business model, combined with also the rising demand for local manufacturing, driven by this geopolitical shift that we are facing at the moment, and I think particularly in defense and energy, it provides a strong foundation for our coming growth. To support this as well, we are deepening our collaborations with both research institutes and also universities, and also expanding our presence in key markets like Europe and North America. But we are also ramping up, as we have explained now, our capacity to provide paid feasibility studies for industrial customers that has the intention to establish serial production through additive manufacturing. So in 2024, we have increased the number of paid feasibility studies with 17 compared to 3 in 2023. So I think that's a significant change. We have also since 2019 already proven the technology to research customers, so our technology for our machines. But in Q3, we installed our first industrial machine, eMELT, which immediately gained interest, but also the trust. In this case, it was in the medtech industry, and resulted in this breakthrough order from one of the global orthopedic implant OEMs, who will run this proof of concept that Per talked through before. So I think this is a major milestone for Freemelt, as the industrial serial producing customer segment will generate the major contribution to a long-term growth target to reach the 1 billion SEK in revenue by 2030, at the 25% recurring revenue from aftermarket. So that's all what we had. So thanks for your attention. Let's open up for any potential questions.
Thank you so much for the presentation here. And as you mentioned, we go straight ahead to the question. I think the first one is for you, Per. You have received an order from the UK to validate your EPBF technology for manufacturing components in tungsten. How long is the validation process for this new customer, and what does it mean?
So if you talk about UKA, the second study, it will be completed this year, and they will do materials investigation, etc., through the first half of next year. But the qualification, that is sort of understanding if the technology is useful. It will be another roughly 2 years before they can qualify the technology.
Thank you. Do you see a possibility of further orders in the future?
Absolutely. But of course, we're not allowed to discuss further orders, but absolutely. And that's what I think I showed also, that we can see when we get upcoming questions, this sort of a latter stage of development is not sort of staying where you are. It is really about how you should move the technology forward to make it possible to use in reactors.
Thank you. I think the next question is for you here, Daniel. How do you see the market situation now that we're soon entering 2025? And are there any sectors you believe in more than others?
Sure. I think the market segmentation focus that we have is on three key areas. I mean, it's tungsten-based applications for defense and energy. And then we have implants within the medical area. And geographically, I mean, we're targeting Europe and US, which is leveraging these high potential regions to drive growth. But the current geopolitical situation is actually giving, or I would say at least the two first, defense and energy sector, tailwind, but also additive manufacturing as such, because it's a lot of focus now on developing and also implementing more innovative and more distributed manufacturing capabilities, which is exactly what additive manufacturing is about. And I think also if we then talk about the third one, implant, I think we can see as well, it's a general more aging and more wealthy population globally, while the orthopedic implant industry also expects a steady increase to be manufactured through AM over the coming years. So I would say that our key focus sectors actually are in positive demand at the moment.
Thank you. During the autumn, you established your first application center in North America. What will the collaboration look like with Harm Industries, and what do you hope this will generate?
Yeah, I think I can answer that one. So if you take Hammer Industries, I mean, first of all, they are a well-known and established company in the US. The location where we have the machine is in Pittsburgh, in an area called Neighborhood 91, which is actually a lot about advanced manufacturing. So with Hammer's experience and also to be an established company here, they have a lot of ongoing business and ongoing discussions as well. So they will identify suitable applications for EPBF technology, where there is a potential for serial production. And what we will do, we will develop those processes and also those applications to really prove the capability to print parts with the highest quality in an efficient way. So I would say it will be a joint collaboration to drive adoption of Freemelt's technology in the US.
I think I can complement that this is also very important when it comes to defense application in the United States.
Thank you. You wrote in the report that of the 20 developed projects initiated during the year, 9 have been concluded successfully and 11 are ongoing. What are the next steps for the successfully completed ones? How many do you expect to move on to the proof of concept phase?
Do you want to answer that, Per?
Yeah, I can try to answer it, because I would say We had 20 studies this year, but I think it's reasonable. Maybe out of 20, well, like 25 to 30% can move to the next step. We cannot expect that everything sort of moves to the next step when we establish the technology. But I say at least 5 or 6 next year is a guess from my side and an estimation. But typically when I talk about tungsten future power plants, it's definitely the case that they're moving forward into the proof of concept state.
And I think maybe also here to add as well, I mean, I think we have shown, I mean, both in UKAEA, where it starts with a phase 1, and then it goes into a second phase. I mean, it can really vary depending on the type of material and the type of application regarding the timing on this as well. But I would say that the likelihood from going from the first study into the second, I think that is really high. Then in the end, of course, I mean, to move more into serial production and proof of concept, then of course it will be more challenging to penetrate that kind of phase.
But each order will be of a higher value and for a longer period of time. So the later stage is almost always of higher income from our side or for our side.
Thank you. Given the timeline you provided in a report, which suggested that the feasibility study and proof of concept phase takes 6 to 18 months to complete, is it reasonable to say there is a potential for eMELT IM sales in late 25?
Yeah, maybe I can answer that one. Yes, I think coming back to the proof of concept that we are now starting with this orthopedic OEM, that as Per said, I mean, that should be ongoing until next year, and depending on the outcome, of course, I mean, then it should hopefully lead to by end of next year that we can see some sort of commitments on orders for the serial producing machine as well. So yes, and of course, I mean, that is one out of others that we have ongoing from feasibility studies that will hopefully move into proof of concept as well. And due to the fact that orthopedic implants is a regulatory industry, of course, then there is a bit of a longer call it confirmation period where you need to go through and get and pass the regulatory bodies as well, which can drive time more. So if you go into tungsten and non-regulatory industries, then hopefully that can also be much shorter phase than others.
Thank you. With regards to the chart you provided in your report on the different stages of customers' development journeys, could you clarify how your revenues and machine sales relate to the different stages?
Regarding what's maybe Martin, do you want to answer?
I can try if I understood the question correctly. So in the beginning, we have the feasibility studies, right? The ones that Per spoke about, and it's small amounts to begin with, or it's we have a margin on those, but it's small amounts. And as the projects move to later stage, the amounts get a little bit bigger, as Per also alluded to. And at some point in time, of course, this is going to lead to machine sales. This is the whole point, and that's where the big money kicks in.
I can add also what you can't really see here. So as far as I know, at least 18 different materials being developed in our customer systems, the Freemelt ONE systems. That can also lead to further machine sales. So these feasibility studies also leads to Freemelt ONE sales, as we also presented that we have 2 Freemelt ONE systems being sold this year, thanks to feasibility studies being done.
Thank you so much. Moving on to the last question here. If Freemelt ONE orders have picked up in recent quarter, what is your view on Freemelt ONE orders going forward?
I can take that one. Yeah, I mean, we haven't shared any kind of, let's say, forecast in the past. We will not do it today as well. But I think what we can start to see, I mean, I think it relates a bit to the feasibility studies increase as well that we talked about today. But also the fact that we now during last year and especially this year, we're still in 2024, so especially during this year, now have implemented a much more structured way of approaching new opportunities. I think we as a company and our technology is starting to become more and more mature as well. So we definitely hope, and we also expect to see that we will get the further, let's say, harvest and more sales for Freemelt One moving forward. We talk a lot about the industrial side, which also Martin mentioned. I mean, that's where the volume sales and also the profitability for us as a company will really kick in. But the Freemelt One will maintain and continue to be a focus for us, because the research side, I mean, we're still having so many opportunities, as Per said, with a lot of new materials, etc. So it will definitely be in focus, and then we should also be able to harvest more and more from Freemelt One sales as well.
Thank you so much, and thank you for presenting here today. Thank you all for tuning in, and I will wish you a pleasant weekend.
Thank you all.
Thank you.